we got two number theory talks in a row here. Today, our speaker is Kenneth Brown, who received his PhD from the University of South Carolina in 2013, studying number theory. He's lived in Sonoma County since then, and he works as a software engineer in the telecom industry at Ciena in Petaluma. Most of his work consists of graph algorithms. His wife Grace is a member of the math faculty here. She's not in the room because she's with their two kids, which is what Kenny likes to do when he's not working or giving math talks. He still tries to find some time for interesting math problems, even if it means giving up some sleep. Today he'll be talking to us about Euler, evaluating Euler sums and subvariants. So help me welcome Dr. Brown.
All right, so I was telling Susan earlier, I'd been working on this problem. I worked on it like a year ago, and then we had a baby, and I kind of got sidetracked for a while. And then, I didn't think about it for a long time, and then I had like an insight, and I figured out like this key step I'd been missing. And so like it was kind of nice having that break. So here it is, it's all fresh. I have the laser pointer, but I don't have the clicker, so I have to walk to my laptop to click. So I guess the background, I'm assuming, is at least one semester of calculus, and if you have 2 semesters, that's super great, but we'll try to cover the necessary background that you need. So introduction. So in this talk, we'll be talking about series and their sums, and these are 2 words you're going to hear a lot, series and sum, and I'll try to make it clear what the distinction is between the two. So if an is a sequence of numbers, you can talk about the sum of terms, a1 plus a2, all the way up to an, where each ak is a number is defined somehow, right? And in this case, the little dot 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 makes sense. You can kind of just say, okay, I'm adding up all these terms, even though I'm not showing you what they are. You're adding them up. But that notation can be kind of clumsy at times. The dot dot dot. So we'll typically use this delimited form, where you use the capital sigma. This is called sigma notation. So instead of a1 plus a2 up to an, you're looking at the sum of the AKs where k ranges from 1 to n. So it really does mean the same thing. This is just a more compact way to write it. So for example, if your sequence of numbers AK is defined to be 1 over k for each k, then this sum AK from k equals 1 to n is just the sigma k equals 1 to n of 1 over k, which is just 1 plus a half plus a third, all the way up to 1 over n. So these numbers right here, these are remarkable enough to give them a special name and a special notation. If you've seen infinite series in calculus, this might look similar to a sort of this one example of a sum that you see called the harmonic series. These numbers we call the harmonic numbers. So there's these partial sums of the harmonic series. And we'll come back to harmonic numbers. They'll be a very important part of this talk. So another very useful example of a series is the geometric series given by, well, you have some real number. In our case, we're saying x is not 1, but you're just looking at the sum of the powers of that number up to some n. The reason I'm saying x is not 1 is because this isn't very interesting. If x is 1, it's just 1 plus 1 plus 1. We can find a simpler expression for this sum. You've probably seen this at some point in a pre-calculus class or a calculus class. But we can derive it. It's a nice little instruction. So if you multiply every term here by x, right, x times s, then you just get x plus x squared plus x cubed all the way up to x to the n plus 1. And you can see there's a lot of terms in common here between these terms and these last terms. So if you look at the difference, s minus x times s, all that's left over is the first term, and then the last term. Everything in the middle cancels out. So if you rearrange and solve for s with this equation right here, you get s is this expression, this nice ratio, 1 minus x to the n plus 1 over 1 minus x. Okay. So all of these series we've seen so far have only had finitely many non-zero terms. You can generalize to talk about infinite series. So if you have a sequence of real numbers, AK, let Sn denote the nth partial sum. So just the sum of the first n terms of that series. If you can take the limit of these partial sums and you get back some number L, then you say that this series is convergent and has the sum L. Right? It doesn't really make sense to add up infinitely many terms. Like, when you have A1 ... up to AN, you can just sort of imagine I'm adding them up, right? But when it's infinitely many, that doesn't really make sense. So you have to look at this limit of the partial sums. So if this limit exists, you say the series is convergent and has the sum L. Otherwise, you say it diverges. Now, you're going to hear these words, series and sum, used a lot in this talk. And sometimes it might not be clear what the difference is, what the distinction is. The distinction really is that when you say series, you're talking about this expression. When you talk about the sum, you're talking about a number, right? So a series can converge or diverge, but a sum is just a number, right? But sometimes the words you'll say sum when you mean series, but it's usually clear from context. You shouldn't get too tied up about the words. Okay, so let's go back to the geometric series. We saw earlier that these partial sums, sum up to n, was just this ratio. And we know from the previous slide that if you can take the limit, and that limit exists, then you can talk about the infinite series. So we can define the infinite sum by the limit of these partial sums. And we know that the partial sums have this nice formula. And this limit, well, we can compute it. I'll show you, right? If x is between 0 and 1 in absolute value, then when you raise it to large powers, it goes away, gets really small, and this term vanishes. If x is bigger than 1, then this term blows up, and it doesn't make sense to talk about. The limit doesn't exist. So we've shown two things here. So the partial sums of the geometric series are given by this nice expression here. If x is not equal to 1, you don't really care about the case where x is 1, plus you'd be dividing by 0. And the infinite series has this nice compact expression. So you've probably seen this in a calculus class. Okay, power series. We're going to generalize a little bit. So many of the functions you see in calculus have what's called a power series representation. Sine, cosine, exponentials. You've seen these. Maybe you called them Taylor series or Maclaurin series. Power series is a very general term. These have the form akx to the k. So you have this variable here. Previously, when you were looking at series, it was just sequences of numbers. But here we have x, a variable. So we're introducing something new. And these ak numbers are our coefficients. So since you have this variable x, you have to be careful when you talk about convergence or divergence. So here's a nice theorem. If there's a number r such that the series here, where I'm looking at the absolute value of the coefficients and r to the k. So here, these terms are numbers. If this converges, then you can say that for all x less than or equal to r in absolute value, this power series converges absolutely. Now that's interesting, right? Because you have this series with a variable in it that converges. So what you're saying basically is that the series that you've written down with the variable converges, and that means that that's a function, right? You can actually use values of x in this range in that series, and it makes sense to talk about. So just to say that again, this allows you to define functions by means of a power series, provided you know that the power series converges, right? So in calculus, you'll study, here's the power series expansion for sine and cosine, and you go the one direction where you have a function, and then you give its power series by doing derivatives and whatnot. But this says you can go the other direction. You can write down some power series, make it up. If you can prove that that series converges, and you can find the interval where it converges, then you can say, well, this is actually a function. And I can do calculus with it. I can differentiate. I can integrate. That's really powerful. So here's a nice theorem, manipulation of power series. So you have a power series. It converges absolutely for x less than r in absolute value. Again, that just means this function makes sense for x in that interval. So that's like the domain you can kind of think of. So if that's true, then your function is differentiable. And you can find the derivative of that function just by differentiating each term in the power series. Okay, that's really nice. You can differentiate term by term. And it has the same radius of convergence. And moreover, you can integrate too. So if you look at the integral of f of x, you just integrate term by term, right? We know the integral of x to the k is x to the k plus 1 over k plus 1 because k is not 0 or negative 1 or anything like that. It starts at 1. So you can differentiate and you can integrate power series. And it doesn't change where it converges. Okay, well, let's see an example. Logarithms. Well, you know from calculus that the derivative of this is 1 over 1 minus x. So I'd have to think about it for a second because you have this negative sign, but the negative signs cancel and you get 1 over 1 minus x. Okay? Now, but we know something about this. We've seen this. That is the formula for the geometric series, right? So what you're really saying here is that the derivative of this expression with the natural log is actually equal to this geometric series. Well, from the previous slide on that theorem, well, we know we can integrate. So if we integrate, derivative basically, vanishes, and then you integrate term by term here, and you have a power series representation for negative natural log 1 minus x is equal to this. And this is pretty simple. You might not expect that it converges to natural log, but it does. This is very useful. I'll go back. This is useful. We will use this several times in this talk. Okay, this fact right here. All right, so let's go back to harmonic numbers. So we defined harmonic numbers earlier. They're these partial sums of a harmonic series. So here's some facts. These numbers, hn, they're never integers, except for the dumb case when it's just 1. But for n bigger than 1, they're never integers. You can prove that. Hn goes to infinity as n goes to infinity. So this sequence, the terms diverge, they go to infinity. And you know that, right? Because you've had calculus, and you know that the harmonic series diverges. This is just the same statement. And you can say a little bit more. You don't need this necessarily. But you know it diverges basically like natural log. And when you're in calculus, you see the integral test. And that's one way you can prove the harmonic series diverges. And this is important. For general n, there's no closed form for the nth harmonic number. So it's not, you can't write it as a rational function, or you can't write it in terms of elementary functions. Right? You have a closed form, I guess you could call it, as a sum, but that's not really satisfying because as n gets large, you have to add up more and more terms. It's not very simple. It's compact, but it's not simple. So there's no closed form for these numbers. But we can find representations of the harmonic numbers that will be useful. So this next trick I'm going to show you is, if you've never seen it before, it might look kind of weird, but it's a really cool trick. And if you take a number theory class, you'll probably use it. So what we're going to do, first, a very simple observation. We know that if you integrate x to the k minus 1 for k bigger than or equal to 1 between 0 and 1, well, it's x to the k over k evaluated from 0 to 1. That's just the difference. And that's just 1 over k, right? That's a very simple observation. Now, we can use this, right? Because we know the harmonic numbers are the sums of these reciprocals, 1 over k. So we can write 1 over k as this integral. Makes sense? Well, this sum only has finitely many terms. Everything is nice. You can interchange the order of the summation and the integration. So this gives us hn is just the integral of these terms, the sum of all these x to the k minus 1. Now, we know what this is. This is a geometric series, so I can write this 1 minus x to the n over 1 minus x. So now I have an integral that gives me the nth harmonic number. It's not a sum. It's not necessarily simpler than that sum, but at least it looks different. And this is a technique. This is a very simple example of a technique that we'll use later. You have a sum, and you want to somehow rewrite it as an integral, or rewrite the terms as an integral. And the reason for that is because, in calculus, you learn all these nice techniques, all these nice theorems for saying, well, this sum converges, but I don't know what the value is. I just know it converges. Or you can say this sum diverges, right? But when it comes to integration, you learn all these techniques, integration by parts and substitutions and trig substitutions. You have all these techniques for actually figuring out what the values are. So if you can rewrite your sum as an integral, it doesn't necessarily make it easier, but it at least gives you a wider variety of tools you can use. So we have this representation, that's what we just had. Now we can do something else to this. We can use integration by parts on this integral, where u is 1 minus x to the n and dv is 1 over 1 minus x dx. So integration by parts, uv minus integral v du. So just rewriting it using that definition. This term actually vanishes when you look at the limits 0 and 1. And so all you're left with is just the integral here. So this is another representation. Minus n integral x to the n minus 1 natural log 1 minus x. So that might look a little more complex because you have a log, but it's another representation, so it might be useful. So let's just summarize what we've written down. We have these two representations. The one nice thing about the second one that we just saw was it had that extra n out front, so you can pull that out, and you actually have an integral for h of n over n. And you can use this. Okay. As was mentioned, next week's talk is about the Riemann hypothesis, the Riemann zeta function. We will be using the Riemann zeta function in this talk, only in its sort of most basic form. Now, for real numbers s, the Euler Riemann zeta function is defined as this sum 1 over n to the s. Now we know if s is 1, that's the harmonic series and it diverges, but in calculus you talk about p series. Right? This is just a p series. I think that's what you probably call them here. This converges if s is bigger than 1. Now, why did I call it the Euler Riemann zeta function when we just called it the Riemann zeta function? Well, Euler actually defined this function, and he studied it 100 years before Riemann. But Euler studied it as a function of a real variable. Riemann studied it as a function of a complex variable, so there's a big difference. But Euler did a lot of really nice things with this function. He found formulas for some special values, and he found some nice integral relationships with it, and we'll be using some of those. So I had to give Euler some credit because he's the one who did the work that we're going to be using. So like I said, introduced by Euler, made famous by Riemann. So Euler computed some values of the zeta function at the positive even integers. Now this looks kind of strange. The zeta of 2n is minus 1 to the n plus 1, so that's just plus or minus 1. b2n times 2 pi to the 2n over 2 times 2n factorial. So these b2n are Bernoulli numbers. We're not going to define those, but they're just a sequence of rational numbers. And then 2n factorial, that just means the product. 2n times 2n minus 1 times 2n minus 2, all the way down to 1. But this is a really cool formula. I'll tell you why. So the Bernoulli numbers begin this way, right? b2 is 1/6. So zeta of 2 is this sum of 1 over n squared. This is one of those things that you see in calculus where you can prove it converges, but you don't know what it converges to. And when I was in calculus, I found that really frustrating. It's like, well, math students were taught to find the answer, find the number, and I can see this thing converges, but I don't know what it converges to. It's really frustrating. But using this formula, you can actually find a nice representation for this. So we use the formula with up here, n is 1, so it's just b2 over 2 pi squared over 2 times 2 factorial. And that's pi squared over 6. Now, if you've never seen this before, look at this. This is mind-blowing the first time you see it. You have this sum of these very simple fractions, 1 over integer squared, and it's equal to something involving pi squared. Like, where did that come from? But that's the truth. You can prove it. There's many, many, many proofs of this. It's such a cool fact that people really like finding new proofs of it. But the important thing is, I guess, for our talk, is that you do have a nice expression for the positive even integers. Positive and even, right? Now, values of the zeta function at the positive odd integers are much more mysterious. For the even numbers, what we just saw, they're all rational multiples of a power of pi. And that's the formula we just saw. They all involve a power of pi and some fraction. But for the positive odd integers, we don't know any values. Like, you can compute it numerically using a computer, and you can say it's, whatever, to 10,000 decimal places, but you don't actually know what that value is. You don't know a single one. And, big deal, we know that zeta of 3 is not a fraction, but that's it. We don't know any other specific cases. There are some weird theorems out there where you can say, like, here's this set of numbers, at least one of them is irrational, or infinitely many of these are irrational, but we can't tell you a single concrete example. Zeta of 3 is the one that we know. So, okay, that's enough for Riemann, but let me just say one little thing, just because I think it's cool. We have to mention the Riemann hypothesis just briefly, just one slide. It states that the non-trivial zeros of the zeta function all have real part equal to a half. So there are some trivial zeros that are very easy to describe, but all the non-trivial ones are on this line of real part a half. And that's what the Riemann hypothesis states. If you can prove this, you will get eternal fame and $1 million, I think. It's one of these $1 million problems. But this is a huge open problem. It has lots of applications in number theory, analytic, and computational. I'm biased because I study analytic and computational number theory, but it has applications in many other areas of math too. But here's just a really cool thing. It's unrelated to our talk, but it is related to harmonic numbers. So this inequality is equivalent to the Riemann hypothesis. So the sum over d, where d is a divisor, that's what that means, d is a divisor of n. If you can show that this sum is less than or equal to the nth harmonic number plus e to the nth harmonic number times the natural log of the nth harmonic number, if you can show that's true for all n, then you've proven the Riemann hypothesis. And it's pretty weird because, like, this doesn't involve any complex numbers. It's just some statement about some fractions and some logs and stuff. But this is actually equivalent. If you can prove this for all n, then you've proven the Riemann hypothesis. Okay, enough of that. Next week is a talk about the Riemann zeta function, and I'm sure they'll go into much more detail. So you should all go. I'm going to try to be here for that next week. Okay, so that's enough introduction. So let's go into some background, what I mean by Euler sums, and what we're actually going to talk about in this talk. Okay. So back in the day, mathematicians, they didn't have the internet or telephone. They would write each other letters. They would challenge each other. Euler got a letter from Goldbach, and the question was, how do you evaluate sums like this? Well, Euler, being Euler, he was able to say something. He was able to give some explicit values for several of these. Look, you have a lot of variables here, right? You have n and you have m. K is our index. But he was able to give some examples in terms of the Riemann zeta function. So I guess at that time it was just the Euler zeta function, but he was able to do it. So for example, this identity, sum 1 over k plus 1 squared times this, which, you know what this is? What is this sum? 1 plus half plus, okay, that's the harmonic number, right? Kth harmonic number. So this sum is equal to zeta of 3. This is really pretty, I think. Zeta of 3 is pretty simple. We know a nice simple sum for it, but this is kind of complex because, hidden here, there's another another like sigma sum going on, right? You have all these dots. This is sort of like that zeta of 2 thing I mentioned earlier. This is a formula that people have found so interesting that they've found dozens of proofs. There's actually a famous paper where they give 32 proofs of this, and they call it the Goldbach variations. And so, of course, I haven't looked at all 32, but there's a paper with 32 proofs of this fact. But of course, Euler was able to do this, and he found some more general relationships too. So over the years, there wasn't really much that was done. I guess I never really defined Euler sum because it's kind of hard to define, but I can just give you a hand wavy. Sums that look like this are called Euler sums. Sums where you have, the important thing is you have a harmonic number, or this is sort of a variant. You have a harmonic number, and you have something that's rational, right? I've only seen one paper where they define Euler sums. It's kind of just this, like, it's an Euler sum because it involves a harmonic number and it looks like an Euler sum. But for our purposes, it'll be a harmonic number times something that's rational. So there wasn't much progress on finding more examples of this over the years. Maybe people weren't interested. Maybe they just didn't know about it because the only example was like in this letter. But there wasn't very much that was done. Until 1948, there was a problem posed in the American Math Monthly to prove this identity. And there was no proof, it was a problem, prove this. So it's 1 over k squared times this kth harmonic number squared. And the claim is that it's equal to 17 over 4 times zeta of 4, which we can use that nice formula to figure out that's a rational multiple of the power of pi. And after this, I'm sure that some diligent mathematicians proved this in 1948, but no one ever published it. No one ever wrote it down. It was just this problem in a magazine. And over the years, I'm sure other people rediscovered it time and time again. But I guess the official proof was in 1993 by the Borwein and Borwein. I think there's maybe 3 Borweins. I'm not sure. So, but the important thing is that they're very prolific mathematicians, the Borweins, and they're very big on experimental math. They've written several books on experimental math, computational math. And so when they approached this problem, they were like, well, what else can we find? We're gonna do these big computer searches and try to find other instances of these Euler sums and try to find what their values are. So your workflow, I don't know what their workflow is, but you can imagine it might be compute a bunch of examples to 100 decimal places and then look really hard at all these numbers and see if you recognize any of them. I'm sure if you do that long enough, you'll recognize, hey, that's zeta of 3, or that's log of 2. But they really inspired people to look for more examples. And so some of the examples that people have discovered since then, I think most of these actually do the Borweins, but 1 over k squared times the harmonic number. The difference here, there's a 2 to the k. It still involves a zeta 3, and it involves this other term. Here's 1 over k cubed, harmonic number squared. This involves zeta 5, zeta 2, and zeta 3. But I think the idea that you're seeing is that most of these sums, well, the ones that we know how to evaluate, usually involve the zeta function. The ones we don't know, who knows? Okay, so most of these identities can be proven by rewriting the sums as definite integrals and then using calculus tricks to evaluate the integral. So we'll demonstrate this technique and we'll prove this identity. This is very similar to the one that there's 32 proofs of. It's slightly different, but if you have one, it's a simple corollary to get the other. I just think this proof is a little simpler. So the sum of hk over k squared equal to 2 times zeta 3. We'll prove this. So we had this representation we found earlier. H of k over k is this integral, right? remember earlier, when we were actually finding this formula, one of the tricks we did was we took this sum and we rewrote the term as an integral, and then we interchanged the order and did some tricks. We're going to do something like that here. H of k over k squared is just 1 over k times h of k over k. So we can rewrite this to be this integral. Okay, that's all we did. We just substituted this whole expression in for h of k over k. There's a minus sign out front now. Now, this step is going to be glossed over, but I will say some words. Interchanging the order of summation and integration gives you this. Now, earlier when we did this, it was no problem. It was a nice finite sum. We can do that. When you have an infinite sum, it's not straightforward to interchange summation and integration. You have to prove that you can do it. But we can do it in this case. I won't talk about it. There will be many times in this talk where I will say interchange, and I'm not going to justify it. All the steps are justified, but I'm not going to show you. So anyway, interchanging gets you this. Okay, so this looks a little nicer, maybe. You have the sum x to the k minus 1 over k. But we saw earlier x to the k over k. We saw that this sum was negative natural log 1 minus x. So if you divide both sides by x, and you move the negative sign over, right, that takes off one of these x's over here, puts a negative sign here. So 1 over x natural log 1 minus x is equal to this. So this integral we can just replace this sum with this expression, 1 over x natural log 1 minus x. And this is what you get. So to summarize, okay, all that was to show that this sum, the sum we want to compute, we've shown that it's equal to this integral. Right? This integral, depending on how much calculus you've studied, this integral might look completely foreign, or it might look easy, it might look hard. I don't know. But it's different. And so we can use calculus tricks. So the first thing we'll do is change variables, x to 1 minus x, basically. That makes things change a little bit, not much, but now it's natural log x over 1 minus x, natural log x squared over 1 minus x. Okay, so you get to a certain point when you're doing math where if you see a 1 minus x in your denominator, you might think, hey, that looks kind of like that geometric series thing. And in fact, it is, so you can do that. Remember, 1 over 1 minus x was this infinite geometric series. So basically, I'm just replacing that part with the infinite geometric series. And that's okay. X is between 0 and 1 here, so like the sum converges, it makes sense. So again, interchanging integration and summation. Now I'm summing an integral. I have a sum where each term is an integral. Now, I don't know, if I just worked in circles, well, if I could evaluate this integral, that would be nice. Natural log squared x to the k. Well, that problem is that k right there. You can do integration by parts repeatedly, and find a nice pattern and prove it. But that's really kind of messy and gross. There's a really cool technique that I want to show you that I didn't know about. I never learned this in college. It's a theorem due to Leibniz. It doesn't look like it would help us. So if you have a two-variable function that's differentiable in t, and such that the partial derivative with respect to t is continuous. Now, what does that partial mean? If you haven't had a class where you've seen partial derivatives, basically, you have a function with more than one variable. You're taking the derivative of the function with respect to just one variable. You're treating the others like constants. So we're doing the derivative of f with respect to t here, and treating x just like a constant. So the derivative of the integral is the integral of the partial. Now, how is that helpful? Well, you'll see. Why was I talking about this so much? Well, it's a really useful tool for evaluating integrals with parameters, right? Our earlier integral had this k, makes it kind of hard. I called it Feynman's trick, right? This Richard Feynman, who was a famous physicist. He actually has written and mentioned this trick before. The story goes that he was self-taught calculus, and he learned this trick, and so that when he was in college, he like had this trick that nobody else knew, and it allowed him to like solve all these integrals that no one else could do. And it's in he mentions it in this book. So you'll see it online referred to as Feynman's trick, but really it's Leibniz's trick. So how do we use this trick? Well, we saw this earlier, right? This simple calculus fact that if you integrate here, you get 1 over k plus 1. Earlier it was 1 over k, but here we've made this k, and that's k plus 1. We know that. Okay. Well, if we differentiate both sides of this, if you differentiate this with respect to k now, not x, you think x because the dx, but no, with k. The derivative of this is negative 1 over k plus 1 squared, and that's just, the derivative of the integral. But that theorem due to Leibniz says that you can write this as the integral of the partial derivative. Okay? Well, partial derivative with respect to k of x to the k power. Well, that x might be confusing you, but just think of it like as 2 to the k, or some constant to the k power. How do you compute the derivative of that? Well, it's just x to the k times natural log of x. Now, if we do that again, we differentiate this side, we get 2 over k plus 1 cubed, and if we take the partial here, you get another natural log. You get x to the k natural log x squared. And this is what we wanted. This is a nice form for this integral that we didn't want to use integration by parts for. So this is what we had previously, and we've just shown that this integral here is 2 over k plus 1 cubed. So that means that this sum we really wanted to do, this harmonic series over k squared, this Euler sum, is equal to 2 over k plus 1 cubed. Now we're summing from 0 to infinity, but we're offset by 1, so that's the same as summing from 1 to infinity with no offset. And this, 1 over k cubed, is zeta of 3. And that's it. Okay, so that's one of those that Euler figured out. I don't know if he did it this way. He probably didn't, but that's one of the ones he figured out. But I wanted to show you this because this is sort of the pattern that I used in the result that I actually proved, and I'll show you at some point. The pattern is take your sum, rewrite it as an integral or parts of it as an integral, do some calculus, jump back and forth, evaluate it. Okay, so let's get to some new results. Oh, do I have any questions so far? Or is everything clear? Okay. All right. Okay, so a little bit more background. So for natural numbers k and n, the binomial coefficient so you'll read this as n choose k is defined to be this ratio n factorial. So that's the product, n times n minus 1 times n minus 2 all the way down to 1. That's k factorial and n minus k factorial. Okay. Now these numbers are everywhere in combinatorics classes when you're counting things. They also have many interesting arithmetic properties, and they come up in power series frequently. And sort of one of the reasons that's true is because of this relationship here, where if you expand x plus y to the n power, you get this sum involving binomial coefficients. And this has a name. This is the binomial theorem. Now, for reasons like this is why you see binomial coefficients appearing in a lot of power series. So the central binomial coefficients, so 2n choose n. If you look at like the list of binomial coefficients, like they start out at 1, they increase, and then they decrease. Like you've seen this triangle of these numbers. So the central binomial coefficients are these guys right in the middle, 2n choose n, right in the middle. These appear in several interesting series. Now what do I mean by interesting series? It's not really a technical term, but it is used in a lot of papers I've found. Basically, it just means it's a series where the terms themselves have easy descriptions, like 1 over k squared, whatever, something that's easy to describe. And the actual value of the sum is easy to describe. So it's written in terms of some constants we know about, or some functions that are like well known. Right? It's really easy. It goes back to that thing you do in calculus where you have a sum that you can show it converges, but you don't know what it converges to, right? It's really easy to just cook up some infinite series that converges, but the value it converges to might be something like horrible and nasty, and you can't write it down. The interesting series are the ones that have like nice, compact, simple values. So these central binomial coefficients appear a lot, and one reason is this power series expansion right here for 2 times arcsine of x squared. This is probably one you don't learn in calculus. But 2x to the 2n power over n squared, 2n choose n in the denominator. And this converges for x less than or equal to 1 in absolute value. Now, why is this so cool? Well, okay, for example, if x is a half, right, then the 2x there is just 1. 1 to any power is 1. So your numerator is just 1. The denominator is n squared, 2n choose n. So it was a power series. By letting x be some specific value, now it's just an infinite series. There's no variable anymore. And we know what that is, right? It converges here. So I know that this is 2 times arcsine of a half squared. What is that? You know what arcsine of a half is. That's one of the things you learn when you do the unit circle. Well, it's 2 times pi over 6 squared. And that's pi squared over 18. So that might be really weird when you first see it. When you see pi squared, you tend to think of zeta. And so this series here is related to zeta of 2. Now, this looked really easy showing this, and it is, but the hard part is showing that this power series is the right power series. Okay, some other, I should say, of interesting series involving the central binomial coefficient. So other good examples are this. So if I have, so let's just back up just for a second, all right? This previous slide, I had 1 over n squared, 2n choose n. My answer involved like a zeta 2. This guy, it's an alternating series. I have an n cubed, and the answer involves a zeta 3. Okay. This guy, it's non-alternating, n to the 4th, 2n choose n, and the answer involves a zeta 4. You can kind of see a pattern. These are all interesting series because the terms are easy to describe, and the values themselves are easy to describe. They're in terms of functions that we know about. You see a pattern. Well, sadly, it doesn't really continue. There are no known interesting series of this form for k bigger than 4. They do know, in the literature, there are some values, like for k equals 5 and 7 and maybe higher, but they're usually pretty messy and not really what you consider simple. Okay, we're jumping right into a new result. This is something that I proved. So k is just this, an infinite sum, 1 over 3k plus 1 squared minus 1 over 3k plus 2 squared. And this looks kind of like zeta. This looks kind of like zeta, right? 1 over something squared. This difference. This constant appears commonly enough that you'll usually see it called k. I don't think it has a name. Some of these constants have names. I don't think this one does. But it usually is called k in different books and papers. So if you have this constant k, then you have the following relationships. So the sum h of 2k over, plus h of 2k plus 2 over 3k over that same denominator, k squared, 2k choose k, is zeta 3. Pretty simple. If you have h of 2k plus 2h of k in the numerator, same denominator in all these guys. If you have this in the numerator, it's 5/3 of zeta 3. And then if you change this coefficient to a 17, you get 5/2 pi k root 3, which looks quite a bit different than these other guys. So something's going on. You didn't change much except for this constant, but you get a pretty different answer. Okay, so let's see how this works. We'll have to prove a lemma first. What am I doing on time? It's 4:45. Okay. So suppose you have a power series that converges absolutely for x less than or equal to 1 in absolute value. Then you can basically insert hk into each term. Into the kth term, you insert hk as a constant. this new power series is equal to this integral. Now you have to be careful. There are some other conditions. You have to be careful to make sure that like these things converge. But this is true. When it is true, this is true. When it makes sense, this is true, I guess is what I should say. In particular, if you let x be 1, which you can do, if you let x be 1, then you get this sum. ak times hk is this integral. Okay, so what does that tell us? Well, if I have some sequence of numbers, so like for example, that example we did earlier, the one I said that Euler figured out was hk over k squared, right? In that example, ak was just 1 over k squared in every single term. And I'm saying with this lemma that that sum is equal to this integral. Well, if you look back, I won't go back because that was a lot of slides ago. If you look back, this integral is very similar to what we actually used to evaluate that sum. This is just a little bit more generalized. So let's sketch a proof of this. This is that representation we used earlier for the harmonic number in terms of an integral. So you have this power series, again, where we've inserted hk into the kth term. Just replacing hk with this gives me this, right? That's just the integral, and the k came out as a negative sign. Again, that trick we like to do is interchange the order of summation and integration. Do that, and you get the integral. Well, this doesn't depend on k, so you can pull it out, and all these terms depend on k. But this might look familiar, maybe not, but this is actually, you see x to the k minus 1, and you see a k out front. That kind of looks reminiscent of a derivative. That's actually just the power series for f prime of x times t. Well, I guess that technically should be a partial, but it's the derivative. So just go back. That's actually what we wanted to show in our lemma, was that this was equal to this sum. Okay. So let's go back to the theorem. We had these 3 sums that we showed these specific values for. Each of those guys involved, at least 2 of these. So A, B, and C. These 3 different sums. We're gonna look at each one of these separately, evaluate each one of those separately, then we can combine those to find the original sums. So, well, the first one, 1 over k, that one that doesn't involve harmonic numbers, that one was done years ago. Actually, I think it was proved before 85. This is one of those results that you'll see. I've seen it in papers from the 70s where, like, they'll say, in personal communication with this other guy, I know this is true, but there's, like, no proof of it. And it's like, well, do I really believe it? I don't know. But this is the first time I've actually seen it. It was in this paper from 85. So again, there's that constant k I was talking about, this difference between these 2 sort of zeta function guys. This sum, this first sum a, is just equal to this value, which has a zeta in it, but it also has some other weird stuff. 1/2 pi root 3k. So it's got some good constants, right? You've got a square root of 3, a pi, and a zeta value, and a k. So really, we just care about b and c, these 2 sums. So we'll just do b, because it turns out that when you have that one done, the case for c almost just falls out naturally. So we'll do b. So that power series we had earlier for arcsine, we've changed it a little bit. 2 times arcsine root x over 2 squared. Now it's just x to the k in the numerator, but your denominator is k squared, 2k choose k. And this converges for x less than or equal to 4 in absolute value, because you've done those variable changes. But you can use this, right? Our lemma says that if we want to like insert hk into the kth term, we have to use that integral. That was what was in the lemma. So this sum, hk over k squared, 2k choose k, is equal to this integral right here, where this f is this guy. And that's kind of got a messy derivative. And this integral looks really nasty. It has logs and square roots and arcsines and all kinds of nasty things in it. But you can do a change of variables and simplify it. I won't show you the details because it's messy and wouldn't be very instructive. But you can do a change of variables. T equals 4 sine squared u. And you get this new integral. 0 to pi over 6 u times natural log 1 minus 4 sine squared u du with a minus 4 in front. This looks really weird. It doesn't look like it's related to like arithmetic at all. It has logs and trig functions and pi. So what we've, just to rehash, what we've shown is that this sum, the one we cared about, hk over k squared 2k choose k, is equal to this. Now, 1 minus 4 sine squared u. Okay, what can I do with that? Well, that actually factors difference of squares. So I can rewrite this as two different integrals, I1 plus I2, where one is 1 plus 2 sine u, and the other one is 1 minus 2 sine u. Okay? Now, when I was first doing this, I was like attacking this guy, and like I couldn't find anything. Like, you know, you have some hard integral. There are these like big books written by Russian guys who just have these, you know, massive tables of integrals, and you know, if you can find it, then you can use it, and or if you can use Mathematica, then you can use that. But like Mathematica couldn't do this integral, couldn't find it in any book or any paper or anything. So this is really where the majority of the work went, was in evaluating these two integrals. But you can see they're very similar. The only difference is the plus sign and the minus sign. So you can generalize, makes your life a little easier. That's what we do in math. You try to generalize and solve the more general problem. So we'll talk about that, but first we need some special functions, and this is where this diverges from calculus a little bit. Some special functions, so dilogarithms. So you'll define the dilogarithm Li subscript 2 of z. You define it to be this integral. So a negative integral from 0 to z of log 1 minus t over t dt. Now this makes sense for all complex numbers z except for the ray 1 to infinity, because log doesn't make sense for negative real numbers. Now this looks kind of complicated, but we actually have seen something very similar to this earlier in the talk. And the reason was sort of hidden to us at the time. This function has a power series expansion, which is really nice. It's z to the k over k squared. That's where that 2 comes from, is it's z to the k over k squared. So this converges for z less than or equal to 1. Now, one thing to note here is that if you let z be 1 in this, if z is 1, then this sum is just 1 over k squared. And that's the Riemann zeta function. That's zeta of 2. So that's where these dilogarithms come into play with the zeta function values. And we can generalize a little bit more. Polylogarithms, these are defined to be the integral of the previous polylogarithm over t. So you have the 2 case as a dilogarithm, and you can generalize these by integrating. Same domain, just because you're integrating. And they have similar power series expansions. The only difference is instead of k squared in the denominator, it's k to the s power. So these are also nice. If you let z be 1, this is just zeta of s. Okay. How am I doing on time? I'll go just really quickly through this. We wanted to evaluate that integral with the log and the sine, right? Well, that was hard to do, so I had to prove a lemma where I was integrating log of 1 minus some constant alpha e to the beta t, right? And that integral is written in terms of the polylogarithm functions. Skip the proof of this. We want to evaluate this. Well, what we can actually do is rewrite sine in terms of complex exponentials. Do that, the 1 minus alpha sine t here looks like this. If you take out a factor, then what you get left over with is actually a quadratic in e to the it, and you can factor that. So this whole thing factors as this product, which is kind of weird at first. But the nice thing is you have log of this is log of this product, and you know log of products you can manipulate those if you verify certain things are true. So we can write this as 3 separate integrals where you just look at the log of each term. Now already you might be kind of like put off because we went from having this integral with like real numbers and real limits of integration, and now all of a sudden we have like logs and complex numbers and things, but it's okay, it works out. There's nothing wrong with going to the complex domain to find your answer than going back. Sometimes it's necessary. So J1, we can just evaluate this directly. It's pretty simple. But these two guys, they are a perfect fit for our lemma. And we can use that for both of those. And this is what you get. You get something involving the dilog and something involving the polylog for each. Okay, so we've evaluated J1, J2, J3. The sufficient conditions are true that we can use the fundamental theorem of calculus and a lot of algebra to show that this integral is equal to this value. So 1/9, 17 zeta 3. You have that k, but you have a 3 pi and a root 3. And the other integral, similar, different coefficients, and there's the same k. And you can combine those, and actually it turns out we did this guy. We showed it was these two, because we factored this at one point. The h of 2k case is already done once you have I1. So doing both of these gets you both sums. And so combining all these, right, you had sort of some messy coefficients here, but when you combine these, you actually get the proof of the theorem that we had. This is just zeta of 3, this is 5/3 zeta 3, and this is 5/2 times this. So that's that. And as a nice corollary, you have values for these sums, which as far as I am aware of, no one has ever computed before. So where do you go from here? Well, if you want to go past what we've done, you can generalize maybe. If you put a 2 to the k here, this is a conjecture, but this is true for like 1,000 decimal places, so there's a good chance it's true. No one knows how to prove it, at least not that I'm aware of. You can maybe insert constantly 2 to the k or a 3 to the k, and you get some different values. These are all considered Euler sums because they involve harmonic numbers. Or maybe you can change the exponent in the bottom. If you make it a 3, this is probably true. It's true for as many decimal places as my computer could handle. And make it a 4 in the bottom. This is true, 11/9 zeta 5. So maybe one of you can prove this, one of these. This guy is, I tried this one, it's really hard. But maybe you have some better insights. That's it. I think all my time is up.
We will be taking Dr. Brown and his wife and kids out to dinner, so if you'd like to join us, come on down front. And if you have some questions, bring them on down front.
I'm here.
Help me thank Dr. Brown one more time.